Good day, everyone. So today we will discuss sample size determination. So let me first share my screen. And this is still under Unit 3 on inferential statistics. And we are in EDUC 321, Statistical Principles and Research Methods in Education. So how important is sample size determination? In the context of research and statistical or any statistical investigation, when we plan for data collection, we reach a stage at which we ask that question or make a decision on how large our sample may be, or how large should my sample size be. For solely descriptive studies, sample size may not be an issue since we just describe what is there and there is no attempt to generalize the results to a bigger population. But for studies that seek to generalize findings from samples to populations, like in experimental studies or in non-experimental studies where relationships among variables are to be generalized, sample size is an important consideration as the results of inferential methods are dependent on sample size. For large surveys, the cost of data collection may be expensive. Hence, sample size determination is critical in a practical sense. When the researcher applies for a research grant, determining the sample size is also an important part of the research proposal because it tells us how much will the data collection cost in terms of time and labor, and that has to be included in the proposed budget. For sample size that are too large may be considered a waste of resources, while sample sizes that are or samples that are too small may be wasted effort since they will be not large enough to detect significant relationships, effects, or differences. So it is important to consider sample size. And there are two considerations, the statistical considerations and the practical considerations. And we strive to make a balance between these two. First and foremost would be the statistical considerations. The study design is the first consideration. In the context of research, there are different sample size approaches and formulas for different study designs or research designs. Sample sizes will vary for experimental and non-experimental studies, and whether you use one group, two groups, or more. Second is the magnitude of the parameter being estimated. Whether it is the parameter is estimated through the mean or a proportion. And the third is the variability of the parameter being estimated. And usually this is measured in terms of the standard deviation. And the fourth is the level of confidence or the level of accuracy and precision in our decisions based on the sample. And this is usually stated in terms of the level of error, with lower desired error rates requiring larger samples. So the level of confidence is 1 minus the level of error, or the level of error is 1 minus the level of confidence. So these two terms are, or concepts are complementary. And the fifth is the data analysis plan. Multivariate analysis requires samples that are larger compared to bivariate and univariate analysis. When we say multivariate analysis, this is the analysis of different variables, several variables simultaneously all together, and they require larger samples. On the practical side, there are three main considerations: the cost, the manpower resources, and time. How much money is available for data collection? This includes funding, if we have a funding research, a funded research, a grant. But even for you who may be doing thesis or dissertations, there is a cost associated, and you may also be considering funding from for those who have scholarships, there is a limitation to the available grant or funding support. Then manpower resources. How many people may be involved in the different phases of data collection? How fast can they work? In research grants, people who are involved in data collection are also given some kind of honorarium, and so there is an entire a cost associated to it. And the third is time. How much time is available for the data collection and for the entire project to be completed? So these are the practical considerations in determining sample size. Now, there are different sample size formulas, and we will base our sample size determination in this discussion on confidence intervals. So the required sample size can be found to reach a desired margin of error with a specified level of confidence 1 minus alpha, where alpha is the level of error. So we have discussed this last meeting on the concept of margin of error as the minimum acceptable or tolerable sampling error. And sampling error refers to the difference between the population characteristic and the sample characteristic. So this is also defined as the amount of imprecision in the estimate of the population parameter. From the computational perspective, we see the margin of error as the amount that was added and subtracted to the point estimate when we formed confidence interval estimates. Do you remember that? That was last meeting. So there are three main factors that we need to know in advance to determine the appropriate sample size. First is your level of confidence desired. So the usual level of confidence may be around 90 to 99%. We can never be 100% confident when we are making decisions based on samples. And alpha here, as you see, is the level of error. So at 95% level of confidence, we allow 5%, now 1 minus alpha, 5% level of error. Second is the variability of the population being studied, usually measured in terms of the variance or the standard deviation for continuous variables, or in terms of proportions for categorical variables. This should be categorical. And the margin of error E, which we have already defined here. So let me just correct this one. This should be categorical variables, not continuous. Okay, thank you. Now let's move to the next. So how do we derive the formula for sample size? For estimating sample sizes where our parameter is a continuous variable and we use the mean to estimate the parameter, we can use the central limit theorem. Do you remember? The central limit theorem says that if random samples of size n, small letter n, are drawn from a large population, then the sampling distribution of the mean is approximately normally distributed, as shown in this graph here, a bell-shaped curve, that's the normal curve, with the mean mu equals mu x bar, that's the mean here of the sampling distribution, and sigma x bar equals sigma over square root of n. This value here below is the denominator is what we call the standard error of the sampling distribution, which is equal to the standard deviation over the square root of the sample size. So you will see here Z as the symbol for the standard normal random variable. As we see here in this graph of the normal curve, the Z is a value that runs from the left, which is we call in mathematics negative infinity to positive infinity. And when we convert the normal distribution to the standard normal distribution, the mean is 0. But we have a specific value of the mean, but any normal distribution may be converted to the standard normal distribution by the formula Z equals X bar minus mu over sigma over the standard deviation. And so we can derive the formula from here, since x bar minus mu in the denominator. So this is actually the difference between the sample mean and the population mean. Mu is actually the sampling error. We write here an absolute value because this sampling error may be negative or positive. The sample mean may overestimate or underestimate the true population mean. And remember, we do not know the value of mu or the population mean unless we examine the entire population, which is not the case. So we are just estimating here the sampling error, the sampling error E. And this is equal to z times sigma over square root of n by some algebraic manipulation of this equation, which leads us to the formula n equals z squared times sigma squared over e squared. If we put this sampling error as e and take the square of both sides of the equation, so the square root of n squared becomes n, and by some algebraic manipulation, we get this formula. So this formula is known to be the mother formula for sample sizes because there are so many other formulas that may be derived from here. So to determine the required sample size, you must know your desired level of confidence, which is equal to 1 minus alpha, which determines the critical value of z. So for example here, at 95% level of confidence, we have a 95% confidence interval. And you see here that z, which is the critical value, is from negative 1.96 to positive 1.96. This value may be obtained in statistical tables, but we can also look at these values as these values upon which the probability is equal to this area under the normal curve. So here you see that if we divide alpha, which is 0.05 into 2, corresponding to the two tails of the distribution, then we have alpha over 2 is 0.025. Okay, from 0.05 divided by 2. So we can find the value of z corresponding to an area below this value. So that is 0.025, that is the area. And that value is z equals negative 1.96. On the other hand, we have positive 1.96 with a value alpha over 2, also 0.025 to the right or above z. So these are our critical values at 95% confidence level. And the sampling error or the acceptable sampling error or the margin of error E is in the formula, as well as the standard deviation. When we do not know the population standard deviation, we estimate and using a sample standard deviation. In some cases, we take the pilot study and take the standard deviation of our variable of interest. So summing up, the mother formula looks like this, no? So based on the given numerical values of the factors we identified earlier, the appropriate sample size is determined by this formula, n equals z squared, and z is the critical value of z in the normal distribution, or we call that also the z-score or the standard normal score. And then sigma squared is the variance, the square of the standard deviation, and E is the margin of error. Now, there are different z-scores for different confidence level, which we can find also again in the table or in the areas under the normal curve. At 95%, we have explained earlier that the z-score is 1.96. At 90% confidence level, the z-score is 1.64, 1.645. That's an area corresponding to the 90% confidence interval. So the confidence interval is shorter compared to 95% and longer at 99%. That's why the z-score here is 2.58. So given these values for z and standard deviation sigma and the margin of error, which is set by the researcher, we can find the sample size. So Sample size determination based on confidence intervals may also depend on the type of variable being estimated. If we are going to use one sample with a continuous variable where mean is used to estimate the population parameter, we use this formula which we have just derived. But if we want to choose a sample where the variable outcome is dichotomous or binary, that is a categorical variable with two possibilities like yes or no, pass or fail, succeed or pass or fail, succeed or fail, something like that. Vote or not, in favor or not, those are dichotomous binary outcomes. There are two possible outcomes in a categorical variable. Then the sample proportion is used to estimate the population parameter. Then the formula may look the same except for the PQ. So here we have Z squared still and E squared, the standard error, the standard score Z, and error, the margin of error E. But instead of sigma, since we don't have a continuous variable, we cannot find the variance or the standard deviation, we use PQ, where P here is the estimate of the frequency of the event, and Q is the complement, 1 minus P. But usually these estimates are expressed in proportions. So we will have an example for these two. First, for example 1, let's make use of the data we had previously on college freshman applicants' IQ scores. Suppose we want to estimate the mean IQ of college freshman applicants to universities using sample data. So the first question here is, if the population standard deviation of IQ scores is known to be 15, so that is known theoretically that population of IQ scores has a mean of 100 and a standard deviation of 15. So that's the theoretical distribution. So what sample size is needed to estimate the mean IQ within plus minus 3% margin of error with 95% confidence interval? So I have made here a table where we will fill in the values of the sample size later. So for the first question, at 95% confidence level, we know Z-score is 1.96 and it is given that the margin of error is plus minus 3. For question number 2, what if we increase the level of confidence to 99%? So increasing the level of confidence to 99%, the Z-score is now 2.58, and we maintain the margin of error plus minus 3 as given in problem 1. And if we decrease to 90% level of confidence, the Z-score also decreases to 1.645, and let's maintain still the margin of error. So meaning we're just changing one variable at a time. We maintain the margin of error and we change the level of confidence, and we will calculate the sample size in a short while to see what is the effect of these changes in the confidence level. However, I asked another question number 3 here. What would be the sample size if we maintain the 95% confidence level as in number 1, but we change the margin of error to plus minus 5? So at 95% confidence level, Z-score is 1.96, but we become now more tolerant. We expand our margin of error to plus minus 5. So to do this, we have the formula here, but I have inputted the formula in a formula sheet in Excel so that it is easier for us. So let us go to this formula sheet here. You have a copy of this. This will be also uploaded in Canvas. So what is needed now is alpha, which is 1 minus your level of confidence. So in the first question, we have 95% level of confidence. So our alpha is 5% or 0.05. Our standard deviation is 15 and our margin of error is plus minus 3. So I have already inputted the results here that the sample size needed is 97. Okay, so actually if you change, for example, the standard deviation to 20, you see this is a function. it changes. If the variability is increased to 20, the sample size is 171. But since our given data says that the standard deviation of IQ is 15, then the minimum required sample size is 97. So let's put that in our PowerPoint here. So you need a sample size of 97. Let me just scroll it down first here. You need a sample size of 97 students for number one. For number two, if we increase our level of confidence to 99%, going back to our Excel, I'm still using the one sample continuous outcome for sample size calculation based on confidence interval. Since our confidence level is now 99%, our error is now 0.01. Okay, so we can change this. The formula is built in. Our standard deviation is constant at 15. Our margin of error is constant at 3. So do you notice these are just intermediate solutions? So the final sample size is 166. So if we increase the level of confidence to 99%, we need 166 students for our sample. What if we decrease? Okay, so decreasing the level of confidence to 90% means the z-score is now 1.645. So going back to our Excel here, at 90% level of confidence, alpha becomes 0.10. That's 10%. 90% confidence level, 10% error. We maintain the standard deviation of 15 and the margin of error of 3. And note, the sample size reduced to 68. So let's again put that there. Let's analyze this all together. Now, let's go back for number 3 question. Let's go back to 95% confidence level, but we will increase our margin of error to 5%. What happens to the sample size? So let's go back here and change our margin of error to 5 plus minus 5. And our alpha is 0.05 because we go back to 95% confidence level. And C, you only need 35. Okay, so let's input that in our PowerPoint here, 35. And let's analyze the results. So let me now put this all together here. And you see, given the same formula, we change our Z, our confidence level, and the Z-score will change. And the margin of error, at first we fix it at plus minus 3. So what do you notice? 95% is the default. It's in the middle of 90 to 99%. No? Okay. So increasing the level of confidence means reducing the error. At 99% confidence level, we only have 1% room for error. And that requires a larger sample of 166. Okay. But if we are more tolerant in our result, that we can allow 10% error, that's 90% level of confidence, we only need a sample size of 68. And if we maintain our confidence level of 95%, but change our margin of error to plus minus 5, we also need only 35 people. 35 lang ang needed sample. So what does this tell us? Sample size is not really fixed. It's not, even if we're using one formula, the value of the sample size is dependent on these 3 factors. So changing any of these 3 variables will change the sample size. Okay, so in actual research, when you state your sample size, you can justify it in terms of your level of confidence and your margin of error. Usually it's the researcher who set the margin of error, but this may be also, the value may be also based on some previously known values. Okay, so isn't that easy? No, so we have different sample size calculator formulas now on the web, which we will also discuss further later. Now let's go to example 2, where this time we're going to estimate a proportion. That's a categorical variable. So suppose we want to estimate the proportion of residents in a city who are in favor of a new city ordinance on local taxation through a sample survey. So how many will be surveyed? So what is the minimum required sample size? A 3% margin of error with 95% level of confidence. This time, we will use this formula. Instead of sigma squared or your variance here, we have PQ. So P here refers to the proportion of residents who are in favor of the city ordinance on local taxation. And if we do not know that, if it is not given, then we can estimate it to be 0.5. Okay, so let us now go back to 50-50%. P is 0.5, Q is 1 minus P, which is also 0.5. So let's go back to our sample size calculator in Excel here, but this time we use the second formula down here on one sample dichotomous outcome here. Okay, let me just check on this one. One sample dichotomous outcome. So what is given is, let me go back, 5% level of confidence, 3% margin of error. So we have 5% level of confidence, 0.05, or 5%, 95% level of confidence means 5% level of error or alpha. Alpha is the technical term for the level of error. So that's 0.05. And if we do not know the proportion of residents in favor of the ordinance, we will peg it at 50-50, so 0.5. P is 0.5, Q is also 0.5, and the margin of error is 3%. Note that in terms of proportion, the margin of error is in percent, or also in proportion, plus minus 3%. So given this, our sample size required is 1,068, meaning we need to survey a sample of 1,068 residents in that city. Okay, let's just put this here in our PowerPoint. So 1,068. Okay, what if we maintain the margin of error but increase our level of confidence to 99%? And then later we decrease to 90%, the same pattern as we did in example 1. So if we increase the level of confidence to 99%, our alpha now becomes 1% or 0.01. Okay, so at 0.01, while maintaining 0.5 and proportion and margin of error is 3%, we need a larger sample. We need to sample or select 1,844 residents. So let's put that here so we can compare this later. 1,844, right? Okay, now let's reduce this to 10% error. So a 10% error, that's 90% confidence level. So 0.10, while maintaining the margin of error. We're maintaining it so we can really see the changes in the sample size one at a time, no? By changing a variable value one at a time. So here we see 752. So if we decrease the confidence level to 90%, we have 10% error level, then we only need 752. So you have that. Now, what if we maintain the 95% confidence level but increase the margin of error to 5%? So let's go back to our calculator here. Our margin of error is now 0.05 because that's 5% is 0.05, but our confidence level is back to 95%, which means 0.05 level of error. Okay? So there you go. We need 385 residents. So in short, let me first put this here, 385. So in short, our decision for the sample size, no, will depend on our chosen confidence level, our margin of error, okay? And the estimate of the proportion. And you will see here differences in the value. These are all justified. If you're doing this in actual research and you are only using 385, for example, as long as you're able to justify that this is the required sample size at 95% confidence level and 5% error or margin of error, then that is acceptable at 385, because sometimes there is a cost associated to sampling. Like for example, when you collect the data and you hire some enumerators to collect the data, and you give an honorarium, for example, in funded research, or if it is, for example, a dissertation and you need some more people to assist you. So we have to be also practical in that sense. So you may not really aim for 1,844 at 99% if 95% is acceptable at 5% margin of error, and you need only 385. But if margin of error is 3%, you have more samples. So you will see here there is a big change, increase, decrease in the sample size when you change the margin of error, much more than when you change the level of confidence. Okay, so that's sample size estimation based on confidence intervals. Of course, if you're doing experimental studies where there are groups, like control, experimental groups, then sample size determination will take a different form. We will use sample size based on statistical power analysis, which we will discuss next meeting on hypothesis testing. So for today, we will just focus on sample size interval estimation or determination based on confidence intervals. Now, there is a more popular formula that some of you may have known. When population size is known, you notice that in the two formulas I presented, the population size may be not known, may be unknown. Like in this case, we may not know the population of residents in a city, and yet we are able to take the sample size. So some have been asking me on this Lovitz formula because it's very popular and it is very easy. Once you know the population size, capital N, and you set a margin of error, which could be 0.05 or 0.01, then you get the sample size. However, in Cochrane's book, research book, social science research book, page 75, the Slovens formula is derived to estimate the sample size for estimating a proportion. So it is based on the use of this formula is based on the following assumption, that the sample was chosen based on simple random sample, and that the population parameter to be estimated is a proportion, with a conservative variance at 0.5 or 50%, with 95% confidence that the estimate is within the level of error E of the true value. So Slovin's formula has a specific use. It is not a one-size-fits-all formula. Okay, but we notice in practice that this has been used in different situations or in different cases because it's easy. You only need to know the population size and you set your margin of error. Okay, so here are some more web-based sample size calculators, and you can explore this further. But for now, we will just focus on Rawsoft as an example. And usually this sample size calculator, especially Rawsoft, is used for surveys. For ClinCalc, this can be also used for experimental studies. So we will use this under a hypothesis testing next time. So let's open Rawsoft and see how it goes and how consistent it is with our sample size calculator formulas. So here we have Rawsoft sample size calculator, and as we have discussed earlier on what is needed to determine sample size, it asks you first, what is your margin of error, or what margin of error can you accept So it says here, it gives you also a hint, no? 5% is the common choice. And there is also an explanation on what is the margin of error, is the amount of error that you can tolerate. And we remember error is the deviation of the true value of the sample value from the true population value. So if we check, no, if we have the same result with this in example 2, at 95% confidence level and 3% margin of error, our formula in Excel gave us 1068. Let us check if this is also consistent in Rousseau. So let's move this margin of error to 3% and then 95% confidence level. We do not know the population size. And it says here, if you do not know the population size, use 20,000. Okay, why? Because the sample size doesn't change much for populations larger than 20,000. So the sample size becomes immaterial. When the population size becomes immaterial when it is larger than 20,000. So the sample size does not change much. And what is the response distribution? That is RP. And it says here, if you do not know, leave it at 50%, which is what we are also doing in our previous, in our other formula. So once we have all this here, we input and it gives us 1014. So there is a little difference, no? What we have here is, let me check, 1068. Okay. Yes, it is possible because it is based on 20,000 here, no? But it doesn't matter much because remember, this is the minimum required sample size. No? So even if we have 1068 here and I would prefer to use 1070, it doesn't matter because that is the minimum. Okay, so there is a little difference in the formula because the formula in Rousseau includes the population size. Although, as I said, it doesn't matter much. And here is there are also alternate scenarios here when you are given the sample size and what would be the margin of error, or when you have the confidence level and what would be the margin of error. So here, at 90% confidence level, 3% margin of error, it's 725. And what we have here, I'm just comparing 752. So very slight difference, no? So what does it tell us? That there is really no one-size-fits-all formula for sample size calculation. So in an actual study, in an actual research, such as in your dissertation or in any funded research in the future, once you declare your sample size, you just have to justify it based on the formula you use and your assumptions on the confidence level you use and the margin of error you use or you select. Okay, so let us continue. Okay, I think this is the last. And the other sample size calculator formulas here, you have the links provided so you can explore them further. And we will use some of them as we move next time to hypothesis testing, where we may be calculating sample sizes for experimental studies or for non-experimental studies that attempt to model relationships, no, for generalizability. So that's all for sample size calculation or sample size determination today. So if you have any questions on this video, we will discuss this further. You prepare your questions for our next class meeting on Saturday, November 27. So that's all, and bye for today. Bye for now.